Here's a habit almost everyone in AI follows. Train a big model first, then squeeze it down afterward so it's cheap enough to run. The trouble is that squeezing after the fact usually costs you accuracy. A 2026 method called CompreSSM from researchers at MIT, the Max Planck Institute, and others asks a different question. What if you compress the model while it was still learning? And it aims that idea at a specific family of architectures, state space models. Let's unpack it. So what actually changes when you compress during training instead of after? Walk through it in 4 steps. Start with what it targets, a state space model. Rather than comparing every token to every other one the way attention does, a state space model streams through a sequence while carrying a compact running state. That makes it naturally efficient on very long inputs, which is exactly why the field has been paying attention to it. Now the usual playbook. You train the full-size model and only then compress it, trimming or quantizing weights to shrink the memory footprint. It works, but it's a separate stage bolted on at the end, and pushing size down after training is already finished is where accuracy tends to slip. Here's CompreSSM's move. It folds that size reduction into the training process itself, so the model is being made smaller as it learns rather than afterward. Because the compression and the learning happen together, the model can adapt to its own shrinking instead of being forced into a smaller shape it never trained for. And the payoff. The model arrives already lean by the time training ends, no separate compression stage to run, and the author's report without the accuracy hit that a post hoc squeeze usually brings. You get an efficient state space model out the door, not a big one you still have to cut down. Now, why does the timing matter this much? Put the 2 approaches side by side. Compress after training, and you're negotiating with a finished model. Its weight's already settled into a large shape, and forcing them smaller means throwing some of that learned structure away. The cut is blunt because the model had no say in where it happened. Compress during training, and the model is a willing participant. It learns inside the smaller budget from the start, routing what matters into the capacity that will actually survive. Nothing has to be discarded at the end because the model was never bigger than it needed to be. Strip it down, and 3 ideas make CompreSSM worth knowing. It rides the state space wave. State space models are one of the leading efficient alternatives to attention for long sequences, so making them smaller and cheaper compounds an advantage they already have on long context work. It changes when compression happens, not just how much. Moving the squeeze from after training to during it is a shift in the recipe, and the claim is that this timing is what lets you avoid the usual accuracy tax. It aims straight at deployment. A model that finishes training already small is easier to put on modest hardware, which is the whole reason people compress in the first place, reached without the extra step and the extra loss. All right, let's lock in what matters. CompreSSM is a 2026 method that compresses state space models during training rather than after, from MIT, the Max Planck Institute, and collaborators. State space models stream a sequence through a compact running state, which makes them efficient on long inputs and a natural target for shrinking. By folding compression into training, the model learns inside its smaller budget, and the authors report avoiding the accuracy loss a post-training squeeze usually causes. The takeaway is that when you compress can matter as much as how much. If you like your AI ideas untangled like this, come spend a few minutes with us at Standarity.com.